So here's a fun gravitational potential energy problem. You want to toss a small ball upward into the air so it finally comes to rest at a height equal to the Earth's radius, 6,400 kilometers. Assuming no friction, how fast must you throw the ball? So when you're given a problem like this, it's a good bet that energy is going to be a good approach. And a diagram is usually very helpful. So I drew Earth here with our guy on the surface, and he's already starting at a distance r from the center of the Earth, which is going to be important, as you will see soon. And it's going to come to a final position that's equal to 2r above the center of the Earth. So one of the critical points here is recognizing that we're measuring from the center of the Earth and not from the center. And for convenience, excuse me, I labeled the amounts of r and 2r because those will go into the equation. So to determine the speed of throw, we can start with the basic conservation of energy situation where the total energy at point A equals the total energy at point B. And then we just kind of have to evaluate what sorts of energy we're dealing with here. Obviously, if this is going to be point A here and point B, point A is going to have kinetic energy. And this is where we have to be careful. We're dealing with heights that are significantly above the surface of the Earth. So mgh is just not going to work. The acceleration of gravity is going to be changing as we get that far away. So we need to use the universal gravitational energy, U with a capital G. And it does definitely have energy at that point here because that is not measured from the surface of the Earth. Now at point B, we're going to have gravitational potential energy, but it will have come to rest, so there's no kinetic. So I'm going to say this is at point A and point B. Then I can expand my equation. K is, of course, 1/2 mv squared. I'm going to call that mass of the object right there. And then I'm adding my universal gravitational energy, which is minus g mass of the two objects, in this case mass of Earth, mass of the object, divided by the radius. And the radius I'm dealing with here is the radius of the Earth because we are right at the surface. So I'll just leave that in as r. And that is going to be equal to the potential energy we have later on at the higher point, at point B, which is equal to g times the mass of Earth times the mass of the object. And in this case, it is now 2r. So looking at the equation, we see that the mass of the object appears in every term, and therefore it very politely cancels out. So let's make that go away. Now I could just plug numbers into this and solve it, but let's just try to simplify things a little bit. I'm trying to solve for the velocity, so I'm going to isolate that and add this term to the other side. Now I have 1/2 v squared equals minus g mass of Earth over 2r, and I'm adding this negative here, so that will be plus, it's very late. I'm adding this to both sides, so that becomes plus g mass of Earth over r. And I could further simplify that and multiply both sides by 2. V squared equals 2, and I'm going to factor out g mass of Earth times 1 over 2r, and that's negative, plus 1 over r. Now I simply have to plug in numbers. Oh, and to solve for v, I'll of course do the square root, and then v equals, this is where it gets nasty because we're dealing with a lot of scientific notation, 2 times 6.67 times 10 to the negative 11 times mass of Earth, which is 5.98 times 10 to the 24, and that is all over negative 1 over 2r was 12.8 times 10 to the 6 plus 1 over 6.4 times 10 to the 6. And if we plug that into our calculator, we're going to get something on the order of about V equals 7,890 meters per second. So hopefully our person has a good pitching arm, because that's somewhere in the vicinity of about 16 or 17,000 miles per hour.